Take a few seconds to look at this video and realize what it is you're seeing here. This is a flock of sheep. And you can probably spot the individual sheep, the individual components that comprise this flock. But the flock is like a fluid that emerges from these components. It's like a new organism in its own rights that can move together in certain directions and avoid barriers. For a single sheep, it might be hard to find its way quickly from one point to another, but once it is surrounded by a lot of other sheep moving in the same direction, it becomes much easier for it to do, and the flock moves together quite smoothly. This is only one example of a much more general theme in nature, where many similar entities join up to create a collective. And these collectives can sometimes give rise to intricate phenomena that the individual component cannot achieve on its own. Only the large collective can do that. In physics, we call these collectives by the general name many-body systems. And many-body systems are by no means limited to groups of living things. I myself come from the field studying nanoscale many-body systems, where the components comprising the collective are tiny particles like atoms or electrons. In a very similar way, these particles can form together a collective that can give rise to a large variety of natural phenomena. And just as a very simple example, you can think of electrons, which are tiny particles carrying an electrical charge. A single electron will generally wander around aimlessly, like a single sheep that doesn't know where to go. But once many electrons are together inside a narrow wire, they form a cloud that can drift from one end of the wire to the other, like sheep running together in a certain direction. This is the simple thing we call electricity. This is exactly what's going on in all the electrical wires, in all the electrical devices that we use. So the fact that the concept of many-body systems is so prevalent in nature motivates us to formulate general theories that will help us to better understand this concept. In physics, when we say we want to understand something, we mean that we want to be able to make quantitative predictions about it. So if we think of the flock of sheep, we want to be able to look at it and have some theory that tells us exactly to what direction it's going to go, at what speed, how the shape of the flock is going to change, and so on. We want to translate this into numbers. And then we can take these numbers and compare them to measurements done in experiments or in nature and check our theory. So suppose now we want to model the behavior of a flock of 300 sheep. We first observe that they are not all the same, right? The left one is relatively younger than the others, the right one is relatively bigger. But these differences are really meaningless if what interests us is the behavior of this new organism, of the collective. So we can start by assuming that all the sheep are identical, and this really simplifies the description. But even then, these identical sheep have some physical features that are irrelevant for the behavior of the flock as a whole. So we can ignore these features as well. We can forget that each sheep has eyes and ears and legs, and treat the 300 sheep as if they were 300 billiard balls. In this way, we have discarded a lot of unnecessary data that would have complicated our calculations. And in return, we got a simplified mathematical model that should be much easier for us to handle. With this simplified model, we now want to perform computations and produce predictions. But once we dive into these mathematical models, we quickly realize that the large collective is still a very complicated creature, even after we simplified the description of the small individual components. Keeping track of 300 billiard balls with all their intercorrelations is a very complicated task, which mathematically corresponds to solving a long and complex set of equations. And such a solution would, if we do it on a computer, for example, would typically require us to store and process a huge amount of data. Going over this entire amount of data is like reading the entire content stored in a large library. It would simply take us too much time. Our challenge is therefore to extract meaningful insights or predictions without reading each and every word contained in this large library. So the traditional approach of many-body physics to this challenge was to devise methods that reduce the initial amount of data we think we need down to a much smaller amount of data. This smaller amount of data encodes the most essential information about the model and is small enough for us to handle and to produce predictions based on it. You can think of it like summarizing a text. Let's look at this sentence on the left, for example. At the present moment in time, it is necessary that he will keep himself situated in the close vicinity of the building. This is obviously overcomplicated, and we can take out from it unnecessary phrases and boil it down to a much simpler bottom line. Now he must stay near the building. this shorter sentence we can analyze much more efficiently, and indeed for many interesting models of many-body physics, it turns out that most of the initial data we think we need is actually redundant and can be discarded, such that we can base meaningful predictions on the smaller amount of data left after this reduction. But now what happens if we try to do the same thing for a different type of text, like this famous sonnet by Shakespeare? Shall I compare thee to a summer's day, thou art more lovely and more temperate, rough winds do shake the darling buds of May, and so on. If we try to apply the same reduction method to this poem, we end up with a single bottom line that captures something from the meaning of the original text, right? But it obviously loses a lot of this meaning and the crucial nuances that the poem had. And there's no real hope, I hope you agree with me, that we can find a single sentence that captures the full essence of the poem. This corresponds to mathematical models where these traditional reduction methods do not work because these models do not contain information that is obviously redundant. So on the one hand, we cannot handle the entire amount of information and produce predictions. And on the other hand, we cannot simplify the data without losing important attributes of the models. At this point, it looks like we must give up on treating these models, even though they are supposed to describe very important natural phenomena. But instead of just giving up, we can change the question that we're asking. This is where my research comes in. In my research, I ask, what makes these two models so different from one another? Why do the methods that worked for one of them do not work for the other? We need to consider their complexity. The poem is inherently more complex than this rather technical sentence. And because we want to be quantitative, we use a subfield of mathematics called information theory. This subfield contains tools that allow us to quantify complexity, such that we can put exact numbers on the extent to which one model or one text is more complex than the other. Using these tools, we can now classify models of many-body systems according to their complexity. And this then raises another question. If we collect all the relatively more complex examples, we can ask whether they have anything in common. So if we think of the texts, we can ask whether do they all use metaphors? Do they all use a high register of language? Do they all discuss the same topics? If we can identify such a unifying feature that is common to all complex models, we can then say that complexity signals this feature, and complexity itself becomes a meaningful characteristic. In other words, what we were trying to do up until now was to study the physical properties and predict the behavior of a many-body system. But then we ran into a barrier. The complexity of the calculation was too high for us. If we now instead study the properties and features of this barrier, this might shed back light on the physical properties of the system that interests us. Studying complexity and its relation to physical properties gets us to a point where complexity comes along with a set of expectations. And to see how useful this can be, you can think of the simple example of renting a room in a hotel. If I rent a room that is very expensive and got a high rating on the internet, I expect this room to be clean and big and comfortable, and I expect this long before I even stepped into the room and saw it with my own eyes. And if I rent a cheap room that got a poor rating, I expect to get much less for my money. So our long-term goal is to build a theory where the system's degree of complexity informs us about its expected physical properties, much like the price and rating of a hotel room inform us about its expected physical condition. In my research, I studied through this new complexity lens basic models of nanoscale many-body systems. For example, my current project deals with this simple model of electricity flowing through a wire. These basic models are quite well known already, but by studying them from this new perspective, we hope to build a theory that paves the way to a deeper understanding of more complex systems in the future. I want to conclude by emphasizing that promoting the theory of nanoscale many-body systems is one of the central missions in physics today. These systems are virtually everywhere, and therefore understanding them better on the abstract fundamental level can lead potentially to considerable progress in the real world. If we better understand the physics of small electrical devices, this can potentially boost the design of new technology. If we better understand biological molecules, which are also nanoscale many-body systems, this can lead to far-reaching implications on the development of drugs. This is the big picture in which I operate, hoping to contribute my share by studying its most abstract foundations. Or at the very least, this explains why counting sheep is actually the thing that keeps me up at night. Thank you very much. these questions.
Hi, I'm Shia. I'm from the Hebrew University. It was fascinating. I'm definitely not a physics, but it was really, really interesting. I have many questions, but I will ask just one. I'm not sure that I understand how you are moving from the complexity index or whatever you are trying to capture to understand the characteristic of the organism, the phenomenon, the whatever.
Okay, thank you for this question. So it's a complicated question. It's very complicated. Everything here is complicated, right? So the idea is to see how we basically what we need to do is to define. Let me start again. Physics is describing natures through some mathematical language. That's, I think, how I see physics, at least. Like seeing patterns in nature and giving them a mathematical language that gives meaning to the patterns that we detect. But math is a very wide discipline. And it's up to us to choose like what specific tools of mathematics we apply to the physical problems we see. So this complexity theory or information theory is actually emerging as a very important language to describe a certain type of phenomena to which we previously didn't have the language to speak. So to answer your question more specifically, it's not like we use these complexity indices to tell us something about the phenomena we already knew how to describe and but we didn't know how to compute. It helps us to define behaviors that we see, but we can't so far put exact names on them. Okay, that's I think would be like answering the question.
Roy from the Hebrew University, thank you. It's like almost a follow-up on the complexity index thingy. You use it as, I mean, you showed examples where you apply it on texts.
Yeah.
But how does it apply on the flock of sheep? And the second thing that when you show, in all examples, I think you showed of higher complexity, these were of pieces of literature, which can be already seen as models of more complicated stuff, right? The Song of Shakespeare speaks about love. It's complicated. It does it in 18 sentences, right? Is it? Can't you take something that is like, you know, maybe bigger? And the question is, are there less complicated texts that yield high complexity index? That are not pieces of literature.
Yeah, this is of course I use the text as an analogy. I'm not aware of like this of actual complexity theory for text. The thing I would so if to answer your first questions about how this applies to the flock of sheep, for example. So I would say like one way there's like information theory is a theory. It's not like a certain measure, a specific measure. You can ask a lot of questions within it. So I can ask, for example, if I let's look at this video again. Why not, right? So okay, yeah, go. Okay, so I can ask like how complicated is this movement of the flock in a sense that if I look at like a certain region of the flock and I ask where this sheep is going to go next. In order to answer this question, do I need to like look only at the sheep at its close vicinity, or do I need to also to look at the like sheep far away, like to have some to be able to allow me to compute this? Like if I want to know the velocity of the sheep, where it's going to go next, how it's going to change, do I need to probe only the velocity of the sheep really next to it, or do I need to probe the velocities of all the sheep in all the flock? What will allow me to compute this, this property that I want? This is one way to define complexity. Okay? You can think of how, or if I apply it to a text, like So you can differentiate between like a book of poems where every poem is complicated, but to understand the poem you don't need to read the other poems. But if I read a novel, then in order to understand chapter number 20, I need to have some context from chapter number 2. Okay, so this like allows me to. It's not you understand. It's not only the scale of the length of the text. It's also like how intercorrelated it is. Like compared to, for example, for a grocery list, where to understand that you need to buy milk, you don't need to know that you need also to buy eggs. It doesn't like you don't need to understand the entire list to understand each item. So that's I hope that. Basically, like it's based on the question I want to answer, whether it's like the spatial structure of complexity, if I talk about more of things that want to that are purposed for conveying information, how much information can I do, like raw information do I need to input so that I get some sensible information afterwards. Like it's a lot of different questions you can ask. Yeah.
Hi.
Where?
Hi.
Oh, hi.
Alon. I'm from law in Tel Aviv. First of all, I can watch movies of herds flocking all day. It's like it is songs in motion.
Yeah.
So but I have it's a kind of a follow-up question about there's the complexity of the movement of the many bodies that move together.
Mm-hmm.
And there's the complexity of the environment
Mm-hmm.
that could be of a different kind of complexity.
Yeah.
And your specific research, is it focused on just isolating the complexity of the movement itself, or about also interaction with the environment, as we've seen in the herds, right? So in the herds, there's what's really beautiful about it is how it changes between different environments and their different complexities, right? So when they have when they go into the grazing, their kind of interaction looks really different from when they're just moving through it through a specific spot, and the entire interaction is different. Also, in our understanding, what are the relevance of the characteristics of the specific, each of the individual bodies and of the interaction of them.
These are all parameters that are crucial and like they are dealt with like a case-by-case basis, or let's say they're all interesting parameters that their influence is interesting to study. Like in physics, we mostly think of, I think if you think of the small passage they have compared to, so we think only about it in terms of dimensions. Whether the movement of the electrons is like one-dimensional, whether they move in, or if I like let them travel in the plane or in 3 dimensions, this obviously changes the question and it raises different questions. So this is, dimension is 1. Indeed, whether the system is what we call, I think, like the influence of the environment in physics, the professional term for it is whether the system is closed or open. So this is an excellent question because one of my true selling points of my research is that I focus on open systems which are less studied in this context than closed systems, which are more well studied. So indeed, like when you have an open system, you have a lot of questions to answer, like whether the complexity you see is due to some internal dynamics of the system or whether it's due to some influence from the environment. And you need to find the right quantitative measures that separate between the two influences and say because indeed the environment can affect this, but usually we know quite well how the environment affects this. So there is complexity, but we know how to decompose it efficiently. And you want to separate between this and the more internal parts,
Yeah, hi.
Yeah.
Doron from the Hebrew University, thank you. I have one broader and one more specific question.
Yeah.
So the broader or more naive is, do you think are there any phenomena that cannot be described quantitatively
Quantitatively.
Yeah, exactly.
It's a hard
Yeah,
word,
it's complex.
Yeah, very much.
Complex word. Or is it just about the overcoming the complexity of the behavior? And the more specific question is, how do you think the complexity index relates to the random factors of the behavior? So, is there room for randomness in the behavior?
You have excellent questions, I must say. So to answer your broader question about is everything quantitative, basically. Like, as a physicist, I'm contractually obliged to say that we think so. I'm not sure. Like, this is more of a, I think, would say a philosophical question. Or like, at what point do we get to the limit of what math can do? I'm not sure. We are like our state of how we see the world is that we think everything can be explained by math, and we try our hardest. And if something fails, that we might need other math, but at some point, sure, it might like, but we also like, we don't try to I think like the deep questions of consciousness and stuff like that, we don't tackle this, right? We try to limit ourselves to the more basic stuff. So I think that would be my answer to that. Randomness is one of it's a crucial component of these studies. Like, a lot of times you have what is called noise or disorder. This would be the technical terms for that. Indeed, for like, so just as an example, I talked about like the sheep being identical, right? So this is a simplification. But then I can, for example, conjure up a model where I have some randomness in their sizes or in their average velocities or something like that. This will induce noise and disorder. I can analyze that. And usually what you do is you introduce this disorder to your model, this randomness, and then you check your theory. Like, this was mostly done by some computer simulations, and then you average over the randomness and see if there are some behaviors that survive after you random out if you average out the randomness, and then you look at this like this. But it's like a huge subfield of what this subject is about. Yeah.
Shachar, I want to thank you. 20 minutes are up. Thank you so much.